Good afternoon, everyone. We are SLAM, which stands for Simultaneous Localization and Mapping. Team members are Aaron Fierce, Ahmad Abdurrahman, Carsey Gibson, Alain Pratt, and yours truly, Robert Jones. The advisor being Dr. Eric Sebron and fifth year PhD student Cameron Lewis.
So the background of our project is using OrbSlam 2, which is a widely employed algorithm for autonomous movement in robotic systems. At present, a big problem present in OrbSlam 2 is the real-time identification and tracking of 3D objects, which is unsuitable for large-scale systems like autonomous vehicles. This processing bottleneck is due to the computational complexities from the full bundle adjustment optimization algorithm of 3D maps. Bundle adjustment is required to reduce the error of projecting key data points from standalone 2D images to 3D spatial coordinates for 3D reconstruction of the scene. And our project focuses on creating a hardware-based graph neural network model using an FPGA to significantly reduce the time and space complexity of the bundle adjustment algorithm.
For our problem formulation, we have our problem statement as of here. And we aim to improve our autonomous vehicle design with the OrbSlam algorithm on either a Raspberry Pi or a FPGA based on the Cyclone 5 architecture. And with this implementation, what makes it different from others is that it's going to improve on the processing time, execution time, and the swap related trade-offs. And it also will prioritize human safety. And in this implementation is very focused on the hardware centric design. And with this, we plan on optimizing the precision and efficiency and navigation. And this will overcome the limitation of software-based approaches. And here we have our design requirements. For our design, we will need an Intel RGB 3D camera, and we will also need the Intel FPGA, and we will also need our Raspberry Pi 3 model. And along with this hardware, we will also need our vehicular frame, the wires that will wire all these components together, a 24-volt lithium-ion battery, and also ultrasonic sensors. Continuing, we are identifying the constraints that this implementation will have. For our environmental constraints, it has to abide by the U.S. roadways, emissions, and also object and hazard recognition. And for our socio-cultural constraints, there's still a distrust in autonomous technology, and also minis have their own vehicle design preferences. And along with this, it will have to abide by the laws of the National Highway Traffic Safety Administration, and along with regional traffic laws.
So our first design for the solution generation involves hosting the graph neural network and bundle adjustment algorithm on the FPGA. The OrbSlam 2 algorithm and vehicle frame, specifically the motors and other circuitry, are going to be managed by the Raspberry Pi 4. The Python programming that will start for the graph neural network and bundle adjustment will be converted to C with Python and then to VHDL through a high-level synthesis tool from Xilinx. Bundle adjustment algorithm will utilize FPGA multiprocessing techniques such as pipelining to receive the simulated results. So the pros of this approach are we have more power efficient design. It's more compatible with our FPGA is more compatible with other components, as programmability is universal for products. It has a high variety of use cases, and it combines hardware design to mitigate software limitations such as time and space complexity. The cons are it's going to be slightly heavier with the added weight of the FPGA. It will require an high-level synthesis tool to convert software language to hardware language, which is not a perfect process, so will require debugging. Has a higher cost point, and it requires both a hardware and software design, so it will require more work from our team. For the second design, this will be a mostly software approach as is traditionally done. The Raspberry Pi 4 will be responsible for relaying data from the RealSense camera for accurate mapping of the environment. A offboard computer will trigger the Python code, will trigger the Raspberry Pi code for execution and facilitate communication with a Bluetooth module. And the Bluetooth module's job is to ensure transmission of commands within the Python script to the Raspberry Pi. The pros of this design are we'll have native Python programming, which will increase the ease of algorithm customization. It'll be more cost efficient. It will be slightly lighter. It'll be easy. The overall circuitry will be easier to make changes to, and it'll be easier to troubleshoot. The cons, it'll be less power efficient. We won't be able to use parallelization for computing processes. We won't be, it'll be incompatible with most hardware components outside of standard GPIO pins available on the Raspberry Pi. It will require triggering via computer terminal offboarding, and it'll be subject to limitations of software processing speed for speed and latency.
So the design that we decided to move forward with, the top solution design, uses the Intel RealSense 3D camera, which records and captures nearby objects, which include possible road blockages such as tree branches, construction, as well as other moving vehicles. And it uses a 1080p camera along with IR radar depth imaging. This uses bundle adjustment. The Raspberry Pi 4 uses bundle adjustment, which processes batches of viewpoints from images to reproduce the most accurate 3D rendition of the image. This leads to location and spatial status of the vehicle, which is then mapped using the 3D reconstruction using the Cyclone 5 FPGA. The ultrasonic sensors are connected to this FPGA, with this power source being the 24V lithium battery. These sensors use sound waves to measure the distance of surrounding objects and sends the response to the FPGA to be processed. This collaboration between the RealSense camera and the sensor determine the vehicle's position and distance in regards to nearby entities. And this data is quickly transferred to the FPGA for a quick reaction of the vehicle to prevent possible collisions. So this is an overall diagram of our final solution design. It entails all the components that are being used on the vehicle and which are connected to which. So this includes ultrasonic sensors, the Raspberry Pi 4, the RealSense camera, the FPGA, as well as the vehicular base. And at the bottom, it describes a more in-depth component list that consists on the vehicular base. So this is where the Raspberry Pi 4 will be operating, as well as the Bluetooth modulator, the FPGA, as well as the ultrasonic sensors.
So in terms of timeline, this project has been ongoing, and we like where we are right now. This is telling what to do going forward. Thus far, we've created the graphical network in Python, we've done the research, identified the problem and solutions, some fundamental challenges and specific design navigation challenges, cloned the SLAM algorithm and put it onto the Raspberry Pi, worked with the Intel RealSense camera to capture footage, which is going to be processed by the Raspberry Pi. We've built the base for the car and created ample room for each of the components to go onto. Going forward, we want to run the SLAM algorithm and get some sample data to see, what the mapping of the environment is looking like. And then going into next semester, we want to have had the Python developed the HDL to be done with hardware, by end of January, early February. They want to place that developed HDL onto the FPGA to be used, in tandem with the rest of the hardware. And they want to establish a strong communication and processing link between the FPGA and the Raspberry Pi 4 by March. And they want to have some practice trials of autonomous navigation, utilizing the local mapping and having some respect to depth perception and the RealSense data to be processed rather, instantaneously or, with very little delay and latency by April, and then by May, we want to have a demo ready, and to navigate, autonomously to avoid colliding with objects that will be, thrusted at it, navigate a course by itself. And yeah. So the intent of our project is to introduce an innovation to an already existing technology. Autonomous vehicle design is not new, and many companies have different designs and attempts at the problem, but none of them have been considered the standard because they don't meet the necessary requirements. Our intent is to meet these requirements by addressing the already existing concerns, which are primarily processing time and power and the speed required to reply to real-time things. That's very that's softwarely computative, requires a lot of power, and just takes a long time to do those calculations in real time. However, hardware, through what Aaron references pipelining, can speed up these processes very significantly and offer, very, very near real-time responses and actually navigate and, safely traverse roads with other drivers in a responsible manner that will actually prevent collisions and accidents from happening. Our design was chosen because it best encapsulates our goals and includes the best parts of both designs while still addressing the initial problem statement, which is to include a hardware-centric design with addressing some of the good software principles that, exist currently in the autonomous design market. Thank you, and that's our presentation.
Thank you.
Thank you.